Okay, starting off with some bookkeeping or explanation. As you know, we didn't have school on Wednesday because there was supposed to have been a huge storm that we got a little of. So I moved both the reading quiz and the homework that was initially due on Wednesday to today. I didn't change the dates until I think Thursday, so you probably, or you could have seen it was due Wednesday and tried to rush and get it done, and then you see, oh, I don't have anything due on Friday. And if that's the case, well, great, you have nothing due on Friday.
Yep, that's my life story.
So just want to make sure that we touch bases on that. It's clear to everybody what happened there. It's because of the snow day. Second, I received an email request to take the exam on the Tuesday following the break instead of on the Tuesday before the break. And the reason for the request was because this person has a lot of tests coming up next week and was, trying to balance the load a little. And I thought I would bring that. I don't want to do one person one day and one person another because, just like this last time, because we had two people who didn't take it at the same time, we had a big gap between when you took the test and when you got it back. I had them graded, but I couldn't give them back to you. And, that's no good. Everybody then, wonders and you have consternation. So I want everyone to take it together, but I thought I'd bring it to the class if you think that's a good idea. Now I will add one more thing. We have everything that I plan to have on the exam done already, right? The stuff we did in the lab on Tuesday is the last stuff that would be covered on the exam if we have it next week. If we postpone the exam until after break, the stuff in today's lecture would also be on the exam, right? I just want to give you enough time to have it processed before the exam is why it would be different. So I want to get students' feedback so I can make a decision that best works for the class. DJ.
Well, my 2 cents is that I would prefer to push it and incorporate this stuff in it so that way it's an easier load for the next test as well. So we can all flow together. And with break, I'll have time to prep it. And I'm also taking anatomy. And this upcoming week, there's 2 tests same day, hectic stuff. So
it is 2 tests because you wrote that. And I was
I wrote the email.
I knew because he had mentioned it a couple of days ago. So I can feel why he's wasting the email. I can resonate.
Mira?
Okay, I had a problem is I have taken 4 education classes and an honors project, and I kind of set spring break aside to focus completely on my education projects. I don't know if I'll have time to study at all for physics over the break, so that's my problem.
Okay.
So if this test is postponed, what will happen to the following test?
No change on that except for the only difference in the following test is that 24 would stay with this test like it was originally planned if we postpone it. Okay. Whereas 24 would be on the following exam if we have it next week.
So if we postpone the test, will the class setup actually be the way it is? Because right now we're doing the material that's not on the test.
The lectures will remain as scheduled.
I mean, but will we be caught up? Because right now if we do the test Tuesday, we are learning stuff that's not.
Given the snow days we've had, we're surprisingly close on schedule.
Okay.
So we're not very far off in our schedule. And the lectures will remain in the same sequence. Chad, you have something?
Yeah, I would like to push this well, but if
he has a quantum mechanics exam.
But I don't know if you're going to do those review worksheets again.
They're already posted,
Okay,
and I was talking to Lydia, and I will by Sunday night have YouTube videos going over the solutions as well.
Well, then people could study ahead of time. I know there's still some capital. It's better than
Medicine.
So if we didn't do this, we'd have 4 chapters on our next test.
I haven't counted them, but we'd have one more than it says in the syllabus.
Yeah. Okay.
Okay, were there other comments? Trace?
If we push it, what are we doing in lab next Tuesday?
What we'll do in lab next Tuesday is the lab is scheduled for the week after. So we moved that one forward.
So would it be stuff on just today cutoff or also all of next week of material?
No, just today.
Okay.
I've made my decision.
Okay, Ryan has made his decision.
I just said I've made my decision.
Any more input?
Be Brian's to offer.
I'm okay with pushing it.
Okay, what I would like you to do is actually, I will put a quiz on Moodle for you to put your input in on. Try to do it today so I can let people know with Moodle announcement over the weekend, so you know how to prepare, right? And I will put there a place for comments as well, because, I mean, obviously, if it's a hardship for Mira, I don't want to give her a hardship. I want to have people's input and try to make the best informed decision I can, okay? And that's why I'm having it a Moodle vote rather than you raise your hand and stuff, because some people will feel intimidated if we just raise our hands. And nobody wants to be intimidated. And hopefully none of you want to intimidate your classmates anyway. TJ's good with intimidation? Okay. So, moving through today's lecture then, what we're talking about today is Chapter 24. Chapter 24 is a link between electricity and magnetism and optics. And so what I have on this picture is the upshot of Chapter 24. That because of the rules regarding electricity and magnetism, James Clerk Maxwell determined that a changing electric field will make a magnetic field, and a changing magnetic field will make an electric field. And when he went through the math, lo and behold, it predicted a wave. And so that wave we call electromagnetic wave, and it has some unique properties because of our right-hand rule relations. And so one of those unique properties you see right here, the electric field crossed with the magnetic field gives you the direction of the velocity. Now, it's not an equality, it's a direction. So the electric field crossed with the magnetic field is in direction of the velocity. The actual relationship, the mathematical relationship, is the electric field divided by the magnetic field is equal to the velocity. The electric field, the magnetic field, and the velocity are all mutually perpendicular for an electromagnetic wave. So as you see me, that means that there is light that is bouncing off of me and going directly to you. So I'll take Ryan as my example. Light from my nose going to Ryan is going that direction. So the electric field has to be perpendicular to the direction my finger is pointing. And the magnetic field has to be perpendicular to the direction my finger is pointing. And in fact, I have to be able to take my right hand and point my thumb in the direction of Ryan, and then my index finger will point the direction of the electric field, and my middle finger the direction of the magnetic field. I can go like this. I can have electric and magnetic fields in all of these directions, but they have to have this perpendicular relationship. So there's some constraints here to electromagnetic waves that we never think about, right? Nobody thinks about these things for light. They just say, light travels.
So your thumb is the V wave? Is that what it is?
Well, that's the way I said, right? Electric field cross magnetic field is in the direction of the
So what is
light.
your thumb?
So the thumb is the direction of the cross product,
Okay.
right? Because that's first item in cross product, second item in cross product, the direction of the result. But you do have to make sure you don't say E cross B is equal to V. No, we don't make the loser sign. Everybody knows which hand you're supposed to make the loser sign with, right? I mean, this is important.
You got to make sure they can read it.
Yes. No. I am sure. This way, you're saying the other person is the loser. If you go like this, you're saying, I'm a loser. So don't do it with the left hand. I won't. These are things I learned when I was in college, and I'm passing them on to the younger generation. Okay. So James Clerk Maxwell. Okay, this is trivial. This is definitely not going to be on the test. Clerk is the family name. Yes, it's not going to be on the test. But I like to make sure people actually understand this because it's kind of a unique thing. His father's last name was Clerk, but his father inherited a estate from the Maxwells and added the name Maxwell to them. So we call these like Maxwell's equations, but you can't forget the Clerk because it's not a middle name. When you see James Clerk Maxwell, it's not like Richard Lee Webb. His last name is Clerk Maxwell. Okay, so James Clerk Maxwell did something amazing, okay? I can't say anything but amazing. When he started working in electricity and magnetism, there was just a plethora of equations. And people had to muddle through all of these equations. You guys have probably learned by now how to muddle through equations, right? Not altogether fun. Not effective? Or not effective? I'm going to go with not effective. I'm not going to put the Lee on there. So James Clerk Maxwell, in 1855, although he didn't publish it for another 6 years, he was able to reduce all of these equations down to just 20 equations. 20 is still a lot, right? And then it took him another dozen years, and he was able to shrink it down, say, all of these equations we have, it's really only 4 equations. Now, the people of Physics 252 can already see a little bit of this because we started with Coulomb's law. And then we learned Gauss's law, and on the test, you had a problem to show that Coulomb's law is just Gauss's law. And then when we got to magnetism, we had Ampere's law, and people in 152 didn't see it, but we had the Biot-Savart law. And we again were able to show that Ampere's law is just the Biot-Savart law. Or the other way around, because it turns out Ampere's law is the one we consider fundamental. So he was able to shrink this down to 4 equations. 4 equations is really manageable, and in fact, it's pretty amazing. Every single thing in electromagnetism can be solved with just those 4 equations. Not easily. Don't get the wrong idea. When I was in graduate school, I really hated that people had come up with things like Green's theorem to make it so an undoable calculus problem became really hard but doable. So it's not easy, but he made it so it was consolidated down as far as possible. So we're going to look at the 4 Maxwell's equations. Now, one thing that has been on the test is how much of Maxwell's equations did Maxwell himself derive? I say a half, because he modified Ampere's law.
What his name still there?
If you look at my 2 slides from now, I call it the Ampere-Maxwell law. I put both of their names there. So, the first 2 laws. The first 2 laws both belong to Friedrich Gauss. Gauss, not Gauss's law is the top one is the one you know. That's the one that says that the electric flux coming out of a region is proportional to how much charge is enclosed. The people in Physics 252 have worked with that carefully. They did some brutal homework with it, in fact, right? So what you guys in Physics 152 learned for Gauss's law was that the number of electric field lines coming out of a charge was proportional to how big the charge was. That's another way of stating it. It's not as mathematically precise, but it's another way of stating it. But then there's the second Gauss's law for magnetism. If we wanted to be precise, we would have said the one we learned was Gauss's law for electricity, or for electric fields. Gauss's law for magnetism, we did not discuss. I mentioned it once. The reason we didn't discuss it is because it's the same law, except for it has to do with magnetic flux. But the problem is, magnets never come in monopoles. You never find a north magnet without a south of equal magnitude. So in any enclosed region, the total magnetic charge is always 0. And so Gauss's law for magnetism, in a practical sense, turns out to say, for any closed surface, the total magnetic flux is 0. That's what it comes out to be, and we don't have any use for that in the physics class at this level. So we didn't talk about it. So those are the first two, Gauss's law and Gauss's law for magnetism. Then we get to the second two, Faraday's law. Faraday's law is near and dear to your hearts right now. That's the law that talks about how you can generate electricity. It's the law that explains why we had the eddy currents to slow the magnet falling. Right? It's really important. It's the fundamental principle behind how an inductor works. So we have Faraday's law of induction. This says a changing magnetic field produces electric fields. And then the last one, the Ampere-Maxwell equation. What you have learned so far was Ampere's law, that says that a current is going to create a magnetic field. And that the strength of the magnetic field can be calculated by doing that circulation, taking the magnetic field parallel to your loop in a closed loop. Well, here's what Maxwell realized. Take the example of a capacitor. If you have a capacitor and you have current flowing, you have current flowing through that wire, then Ampere's law says, I take my right hand, I put my thumb in the direction the current's flowing, and I'm going to have a magnetic field that's doing a loop around the wire. And if I'm charging the capacitor, I'm going to have current flowing to it on one side, current flowing away from it on the other. But what do I have between the plates? I have a field that's building. I'm building an electric field here. There's no current here because there's no charge passing from one plate to another. And so if I were to apply Ampere's law in this region where there's no current, that would say no magnetic field. Does that people follow that? But what Maxwell realized was, wait a minute, nowhere in the description, okay, I can't erase those for some reason. Nowhere in the description does it say how you determine how much current is going through your loop. Basically, you could treat the way you determine how much current is going through your loop by saying, okay, let's take a bubble. So I have like a blowing bubble thing. And if I put it so it's just flat here, the wire goes right through it. But if I blow the bubble, I can make the bubble so it comes out like this. And so I can have my loop over there on the left, but have the bubble coming out and going like this. How much current then is going through that bubble? Right, the wire is not touching that bubble. So how much current's going through it? 0. And so Maxwell said, well, if I take Ampere's law and I decide to deform my bubble where I'm calculating how much current goes through, I end up with no current and no magnetic field. Well, that doesn't make sense. It shouldn't be, well, I decided to calculate differently, so I got a different magnetic field. Right? You can't physically change the outcome because you decide to calculate differently. And so he said, there must be a missing piece to the puzzle. And so Maxwell said, well, we're going to be building an electric field in here. Right? If we have a capacitor plate, then we have the electric field strength between the plates is equal to the voltage difference over the separation. But the voltage difference relates to the charge as Q over C. Q is equal to VC, yeah? So the electric field is going to be the charge on one side of the plate divided by the capacitance and the separation of the plates. And so he said, okay, so if I had current is delta Q over delta T. So I'm just going to take that equation and say delta E over delta T is equal to delta Q over delta T times 1 over CD. And then taking the definition for capacitance, capacitance was epsilon A over D. Those D's cancel. And what I have is an electric field changing as there is a current flowing. And so he said, let's just call this I displacement is equal to the delta Q over delta T, which would be epsilon A change in electric field over change in time, which I believe I did correctly. And so the final form is, it's epsilon change in electric flux over change in time. Does somebody see the one difference between the work I just did and the work that I had typed out? I have one equation on top of the other.
DT?
It's what?
You didn't cancel out the D's on the last one.
Okay, well, these are a different D. This is calculus D. This D, I didn't even recognize that as a difference because this is delta. This D means delta for very tiny change.
Okay.
And so in my brain, those were still the same.
Okay.
I'm so sorry, it's a calculus thing. The one difference here is I have a 0 here. I don't have a 0 there. That difference is if it's in vacuum versus if it's in something other than vacuum. And so technically this is actually more correct. Because this is for any situation, this is only if it's in vacuum. But nonetheless, this current, Maxwell said, there is a equivalence to a current flowing if you have a changing electric field. And so he called that the displacement current. As with many things we've learned recently, the name displacement current doesn't work. The theory he had that gave him the word displacement turned out to not be right, but the current calculation was right. And so what he did is he modified Ampere's law to say that, remember, it was the circulation. So for our class, we put the sum of the magnetic field dotted to the change in the length as you go around a loop was equal to mu. And once again, I'm going to drop the subscript of 0 just to make it as generic as possible, times the current enclosed. And so that would be the current plus this displacement current. And so that's the outcome. A changing electric flux produces a magnetic field, just like a current does. But that was a really, really key difference because this says a changing electric flux creates a magnetic field, but we already had from Faraday's law of induction that a changing magnetic field produces an electric field. So now we have a situation where one changes, it creates the other, but its change creates the first. That's the kind of thing where we can transfer energy back and forth. And so, and we will do this in class on Tuesday, oh ye calculus-based physics students. He was able to take these 4 equations and combine them to come up with a wave equation. Here are the 4 Maxwell's equations written in 2 different forms. Notice they are calculus equations. The left form is called the differential form. It has derivatives. That upside down triangle is a directional derivative. It's the change in whatever is falling, so change in electric field, with respect to position. And it has X component, Y component, Z component. So for a non-calculus student, just read this as delta E over delta X and be done with it. It's not what it really means, but it is a three-dimensional variation on that. So the spatial change in electric field has to do with rho, that's the charge density, how much charge you have per volume divided by epsilon. And once again, this has 0, so it's in a vacuum. For magnetism, it's equal to 0 because there is no magnetic monopole. And then we have this here, that's more complicated. Notice it's a cross product instead of a dot product. It's still a change with regard to direction, but it's more complicated because of the cross product. So a time change in magnetic field produces an electric field, and this last one here, a time change in electric field produces a magnetic field. The second column is the integral form, more calculus. If you integrate both sides of the equation on the left, you get the equations on the right. And what we actually learned in this class was the integral forms. This here was the electric flux is equal to Q over epsilon 0. I don't remember why there's a V in parentheses there. And this one here is the magnetic flux on a closed surface is always 0. And then this here is the induced voltage. I'm going to put EMF just so we realize that's not talking about epsilon. And this one here, that's what we call the circulation. So the ones we learned in this class were the integral forms, but we didn't learn them with the calculus symbols. That is all of electricity and magnetism on this page. Duplicated. It's all of electricity and magnetism twice, once in a derivative form and once in the integral form. So you know that physicists have the best senses of humor around, right? Right. So we do things like we wear shirts like this. God said. And then we have Gauss's law for magnetism. And we have Faraday's law and Ampere's law. And there was light. Now, I want to take a moment to tell you I believe this to be true. I believe that God created this universe. But I believe that he started by creating the laws of physics. And so he made these laws, and then he put energy into the universe, and then things have developed from there until he created life. That's my personal belief. And so this here is it's what I believe. God made the laws of physics, and then he put the energy in for the universe to exist. And so this shirt, while it's generally worn by people who are kind of mocking God, I believe is truth. So I have to point this out because, well, you know I'm a true believer. Why else would I work here? And I have a second shirt here. What's the difference in the two shirts?
The style of the notation.
Yeah. This is the derivative form on the left side, and it's the integral form on the right side. Okay, so we physicists, good this way. We got senses of humor, like all kinds of things. So, to make sure that you followed questions up to this point that would be on the test would all be conceptual, right? There's no math that we've done here. What we have is that Maxwell took a whole bunch of equations and condensed them down to how many? The 4 equations. And those 4 equations can be used to describe all of electricity and magnetism, and they predict that there's an electromagnetic wave. 84, by the way, that's just the year I graduated from high school. It's 35 years this year. Good times. How many of Maxwell's equations did James Clerk Maxwell recreate on his own? Part of 1. So why does he get the credit if he only made 1/8 of the Maxwell's equations? Because he was able to simplify it. It's a great act of genius to do that. So he rightly gets the credit. This isn't some fluke like, well, you know, right place, right time. You know, he did some amazing work. So let's talk about some ramifications of this. I have this device, which according to my wife, I used way too long. Oh my goodness. New England Patriots owner Robert Kraft charged with soliciting prostitution. Couldn't happen to a less classy guy.
Got him.
True story. At another institution I used to work at, we had a religion professor who was arrested for solicitation not once, but twice. Yeah.
That was real.
So, yeah. Well, there was the president of one of our Adventist colleges who was in a really ugly case of the prostitute robbed him.
Robin twice in that case.
So, what is a real world example? I have my phone. I'm sorry I was distracted by that news. This phone is communicating via electromagnetic waves. This phone is made possible because of what we've learned from James Clerk Maxwell's work. And so the important things that allow me to use this phone, well, they were listed in those 4 equations. And we have some important things to help us get the thought straight and how it works. So, an accelerating charge produces an electromagnetic wave. If I have charge that's changing speed, it's going to have then a changing magnetic field and an electric field. It's going to make the electromagnetic waves. A point charge, if it's stationary, is only going to give an electric field. If it's moving at constant speed, it's going to have a constant magnetic field. You need to have that acceleration. So we make electromagnetic waves by having charge oscillate or move. So here is an example of making an electromagnetic wave. So I'm going to have here an antenna, and on the antenna I'm going to have, let's say, positive and negative there. So what are electrons going to do if I put positive on the bottom and negative on the top?
They're going to flow from the bottom to the top.
Okay, so I'm going to have electrons flow from the bottom to the top.
Oh, from the top to the bottom.
I'm going to have electrons flow away from negative and toward positive, which means the current, which is probably what you were answering, the current is going to be going up. So that would create a current that goes like this. And if I have a current that direction, then it's going to make a magnetic field. I take my right hand, put my thumb pointing upward, my fingers wrap around, it makes a magnetic field. And then if I reverse the where's positive and where's negative, it's going to reverse the field. And so my field, my magnetic field will change directions as I alternate which side is positive and which side is negative. And at the same time, if I have, I forgot which one I put as positive, which one's negative at this point in time. So I'm just going to go with the signs it has here. I think that's what I had. If I have negative at the top and positive at the bottom, that's also going to create an electric field that points that way. So I'd have electric field that's vertical. Magnetic fields are going around in circles. Now we learned that I can have an electromagnetic wave with its velocity such that the electric field across the magnetic field is the direction of the velocity. And so if my index finger is up and my magnetic field is going like this, then I can have an electromagnetic wave going out perpendicular to those two. And so that's going to create electromagnetic waves that are going like this. So this antenna, if the antenna was of infinite height, it would only make waves going out horizontally. In fact, we use this to our advantage. When I was a child, my grandmother and grandfather, they leased out a portion of their property to a radio station that had these towers in the ground. And all I knew is those were grandma's towers and they were something for a radio station. Well, those towers were making electromagnetic waves that were going out horizontally. It's kind of what you want with your radio station. You're not so interested in the people up in satellites listening to your radio station as you are people on the ground. Now, furthermore, their field had 3 towers. The reason for 3 towers is because when you have waves, you can have constructive interference and destructive interference. Remember, we talked about that with sound waves. We have the same with the electromagnetic waves. And so with these 3 towers, you can adjust the phases, the time when you're at peak for each tower, so that you, for instance, might make the electromagnetic waves go really strong out this direction with nothing at all going this direction or this direction. So that you're only shooting, Modesto is in the Central Valley, you really only want to shoot up and down the valley. You don't want to shoot to the mountains so much. So they used the multiple antennae so they could control the direction. Now let's take this to something that's a lot more near and dear to your hearts probably. Cell phones. We like our Wi-Fi connection, right? We have a Wi-Fi connection here in the room. And where is our Wi-Fi signal coming from? See the back corner? That's where it's coming from. No, Ryan, because you're not using your phone during class, remember?
Right.
Keep telling that.
That's where he takes his notes.
Yeah. By the way, I should point out, if we postpone the test until after the exam, the scrapbook would also be postponed. Yes.
Question on that. So if we've already submitted it and it doesn't include 24, is that okay?
That's fine. Yeah. If it's just 23 and 24, that's fine. You don't have to include 24 in it. But if I'm only going to be grading ones from 22, or I said 22, 23, and 24 is all I'm going to be grading. Yeah.
So when will we know if it's postponed?
I will let you know. After class, I will put it up on Moodle, and then let's say by 5 o'clock tonight, I will close it. So you don't have a lot of time. So make sure you get to it. So I'll let you know before sundown tonight. I don't want anyone studying on the Sabbath, but I will let you know before sundown.
That's the poll, the little quiz thingy about.
Yes, yeah. Okay, so back to this. These days, when you buy your little Wi-Fi adapter for your house, it comes with, it looks like a spider, right? With a whole bunch of antennae. It has all those antennae because it uses smart signal generation to determine where your phone is and adjust the phases from those different antennae so it makes a beam going to you and not wasting power going to the rest of the house. And so when multiple people connect, it will actually make different beams. That's why you have all of those different antennae so you can make the different beams. So we can make electromagnetic waves and we can do crazy things to manipulate them with these towers. And so here is a simple dipole antenna. Now, this here is the basis for the testing of Maxwell's idea that there is such a thing as electromagnetic wave. Right? What Maxwell did was Maxwell took those equations, like we're going to do in class on Tuesday. If you guys want to come and see how it's done, we'll be doing it Tuesday, 11:30 to 12:20, right? Well, Maxwell did the calculation. The calculation gave him that it supports a wave, and not only that, it said the wave would have to have a speed that's 1 divided by the square root of epsilon mu. That is, Maxwell's equation said I'm going to put zeros and zeros, so the speed in vacuum would be that. And so, of course, any person can say, I wonder what that number is. And he calculated, and it was the speed of light. And he said, whoa! There should be an electromagnetic wave with the same speed as light. Light must be an electromagnetic wave. That's kind of like me saying, whoa! DJ runs the same speed as that car. DJ must be a car. Yeah, it makes as much sense. But that's what he said. And so what are the other scientists going to do? Well, they're going to prove him wrong. Of course, that's what we all do in science, right? You do an experiment even to prove yourself wrong, right? You have a hypothesis, it makes predictions, and then you do a test that could disprove it. And so Heinrich Hertz is the one who did the important experiment where he used a spark gap generator. That is, he basically had two balls, and then he had an AC or a power supply, not an AC power supply, but a power supply. The voltage would build up, then he would have an arc go between them, and that's how he made his electromagnetic waves. This here is a simpler form where instead of having the arc here, you have these antennae, and you just have your power supply going to those antennae. Antennae, by the way, is the plural of antenna, in case people are getting confused about the words I'm using here. And so you go positive to negative, and it makes the current go back and forth, and it makes the electric fields go back and forth, like we already talked about. So Heinrich Hertz is doing these experiments, and he says, okay, I've made electromagnetic waves. I can detect them, using an antenna like this and measuring, hey, if there's an electromagnetic wave coming, it should create, if there's an electric field, it should make current flow because electrons are going to be pulled toward the positive side and pushed away from the negative side. So he measured the waves, and then he tested to see if the waves followed principles already known that light did. Things like, okay, so these are words coming up next week. Refraction. Light bends when you go from one material into another. It's called refraction. So he tested to see if these electromagnetic waves would bend when they go from one material to another. They did. Diffraction. This one's a little surprising. Light bends around corners. Everybody knows if you watch a water wave that it bends around a jetty. Or if you have the door open, somebody's out there in the hall, the sound will bend around even though you can't see them. But we don't tend to think that light bends. If I go out there and stand in the middle between the two doors and have the doors open, you don't see me. And so you say the light must not have bent. But it does bend, it just bends a lot less. And so he was able to see that electromagnetic waves do that. All of his experiments showed that electromagnetic waves had the same properties as light waves. And so based on Heinrich Hertz experimentation, then scientists accepted that light was just a form of electromagnetic waves. Now, before I get too high and mighty on this, I'll talk about that in a minute. Before I get too high and mighty on this, I'm going to point out one of the confusing matters in optics. As far as I know, the earliest theory of light, or our vision actually, I read this in a book, so I take it as the gospel. I hope it is because it's great. Was the Tentacle Theory. The theory that I can see because I have these little invisible tentacles that are coming out of my eyes, and they go out and they touch things, and then I perceive them because of the touching of those tentacles. Which I know is kind of a creepy picture, but what worries me is I could totally blind myself by going like that, right? I could cut off all those tentacles. That would be bad. Well, different people came up with different theories of light. And one of the earlier theories was the corpuscular theory, that light comes in little packages. This is something that Isaac Newton believed. And Isaac Newton worked out some good optics for light coming in these little packages, like BBs. But then Thomas Young did an experiment we're going to learn about where he showed that light interfered with itself. That is, if I have light and I have two slits, the light going through the slits, instead of making two bright spots, we'll make a whole bunch of alternating bright and dark spots, which can only occur if it's a wave. And so after Thomas Young did his work, everybody's all, okay, light's a wave, not a particle. We were wrong. Newton was wrong. But then we have what we'll learn from Max Planck and Albert Einstein. Albert Einstein said, no, light's a wave. And he came up with an experiment, one we call the photoelectric effect. It's an experiment we're going to do that showed that, or not a wave, that light's a particle, that showed that light clearly behaves like a particle and not as a wave. So we have actually two experiments. Thomas Young's double slit interference experiment that says light can't be particles. And Einstein's photoelectric effect, which people will point back to the work of Hertz as the first observation of this, that says light can't be a wave. And so what do we as physicists conclude?
It's both.
That it's both. And that is so troubling. It's both a wave and a particle, and depending on what you're looking at, it's going to show one or the other, is what the official story is. And I believe when we get to heaven, we're going to find something different. We don't understand it fully yet. Yes?
What was Einstein's experiment with photoelectric?
It's called the photoelectric effect, yeah.
What did he do?
Okay, so the photoelectric effect, it is known that if you shine light on a surface, electrons will come off. So we call those photoelectrons because they came off because of light. And Einstein said, okay, if light's a wave, then what's happening is you have the energy from the wave is being absorbed by an electron. And so you get enough energy in that electron and it can break free of the surface. And if it's a wave, the amount of energy absorbed is going to be proportional to how bright the light is. Brighter light is more energy, so you're going to have more energy absorbed. And so you make the light brighter, they should come off with more energy. That's the wave theory prediction. The particle theory prediction, the one that Einstein was championing, is that the light is coming in little packets of energy. And so an electron is, unless you have super intense light, it's only going to get hit by one packet of energy. And so no matter how bright the light is, the electron's only going to get the energy of one packet. It's going to come off with the same energy. And the only way to change the energy of the electron is to change the energy in the packet, which is proportional to the frequency. So if you change the color, then you should be able to have electrons come off with more or less energy. But changing the intensity will only change how many electrons come off, not how much energy they have. So that's what the photoelectric experiment is. And when the experiment is done, sure enough, the energy of the electrons has everything to do with the frequency and nothing to do with how bright it is. And so that says it can't be the wave theory, but it's consistent with particle. Remember, we can't prove the particle. So it doesn't prove the particle theory. It proves the wave theory wrong. But then Thomas Young's experiment proved the particle theory wrong. And so we have proofs that both of these are wrong, so we just believe them both to be true.
And the combination of them is called a photon, right?
No, the photon is the name of the particle.
Okay. So there's just no name for light.
Well, it's a wave. Yeah, there's no special name for the wave that I can remember. It's a what?
It's a photon wave.
Good thinking, Trace.
That's how we get into science class.
The photon wave. Okay. So, practical use. Kids these days don't have the experience with antennae that we had when I was a child. When I was a child, we had television. Well, when I came to America, we got a television set, gotta get this cool new thing. And the television has the rabbit ears on it. And those rabbit ears, of course, none of us had any knowledge about antenna theory. We just knew that you rearrange them and the signal gets better or worse. And after a while, you learn, if I want to watch KSBW TV8, I'm going to have them like this. And if I want to watch Channel 46, I need to have them like, this. And you learn the different configurations for the different channels. And probably none of our configurations were ideal, but we went with what we learned. Well, here's the way it really should work. You should ideally have one of them perpendicular to the other. Because one's the ground plane and one should be parallel to the direction the electric field is oscillating. What direction is the electric field oscillating? It actually depends kind of on your location. So if you have the antenna that's parallel to the field, then you're going to have the maximum electric field alignment with the charge and the maximum then force along the antenna, the maximum current produced in the antenna. Because that's all you're doing with the antenna, is you're making a current by it responding to the electric field in the electromagnetic wave. And the ground plane is just, for the comparison. So you're going to have best reception when your antenna is parallel to that electric field. And it's just, as we've learned, force is equal to QE. That's what's making it work. So let's see, is somebody making a radio receiver? Yeah. And so you have an antenna, that's what's going on. Now there are other things involved with antennae, like how long should the antenna be? There are rules for that. The longer it is, the bigger the current you can make, but if you have the wrong length, you'll have destructive interference as well. So it gets complicated. There is a second type of antenna. We had these for things like radios. So we have the rabbit ears that we use for the television. And then here is something that still today comes with a radio that you buy. Oftentimes you'll have a loop with a whole bunch of wires going in a loop. At this point in time, you've learned, if I have a whole bunch of wires going in a loop, what is it going to be detecting? What will cause a current to flow in wires in a loop? According to Faraday, a changing magnetic flux. And so with this antenna, you want to orient it so the magnetic field lines are going to be going into and out of the loop. And then the changing magnetic flux induces a current in that, and that's the signal that you amplify. So it's a fundamentally different type of antenna. This is a magnetic field antenna, whereas this here was an electric field antenna. And we're out of time, and I'm out of slides. It's all perfect. I will go put up that quiz question within the next 10 minutes.